Yeah, thanks, Tanase. So, so I'll be talking about hyperbolic surfaces in this course. So let me set up some notation. So throughout this series of talks, by surface I will mean a compact, oriented, connected, smooth surface. Okay, and such a thing is, as you know, is specified by these two integers, the G and B. So G is the genus, and B is the number of boundary components. Okay, so that's what this notation will stand for. And so here's an example, is a picture, just to have a picture. So this is something which is S22. And the Euler characteristic of such a compact surface is 2 minus 2G minus B. Okay, so you take a closed surface of genus G and remove B disks. And so the starting point for us is the following fact, that if the Euler characteristic of a surface is negative, okay, so I'll sometimes drop G and B when I don't want to specify what they are. So if the Euler characteristic is negative, then there exists a hyperbolic metric on S. Okay, and you've already seen what a hyperbolic metric is. So a hyperbolic metric is some Riemannian metric with constant curvature -1. Okay, you can think of it as being modeled on hyperbolic plane, okay, H2. And for us, we have these boundaries, so we would require that these boundary components are geodesics. Okay, so this is what I would mean by hyperbolic metric on such a compact surface. Now, the fact that this Euler characteristic of the surface is negative is a necessary condition. This is easy to see. This follows from Gauss-Bonnet. Right? After all, if you integrate the curvature over the surface, you would get something negative, and so then that's 2 pi times the Euler characteristic. Right? So that's necessary, and in fact, so once for any such surface, there exists hyperbolic metrics, and that we'll see today. So today we'll construct. I'll tell you about how to construct hyperbolic metrics on such a compact surface. Okay, on SGB, and in fact, our construction will cover all possible hyperbolic metrics, and that has a name. That space of all hyperbolic metrics on S, together with something called markings, which I'll say what they are, but that's called Teichmuller space. So I'll introduce Teichmuller space, the space of all these hyperbolic metrics. Okay, and the goal today is to show that this Teichmuller space, T of SGB, is actually homeomorphic, so equal to the space of dimension as a cell of dimension 3 times the absolute value of the Euler characteristic. Okay, so here S is just SGB. Okay, so that's the goal for today. So just to look ahead, so lecture 2 tomorrow, I'll talk about somewhat the algebraic viewpoint. So one can also view Teichmuller space or points in Teichmuller space as kind of representations of the fundamental group of the surface into PSL2R. So that will be the sort of the groups component. So today is the geometry, and the sort of the last day 3, I'll talk about the dynamics of the. So I'll talk about the mapping class group action on Teichmuller space. Okay, and we'll see that this is. Interesting. So it turns out that the quotient of Teichmuller space under this action is what is called the moduli space of Riemann surfaces, so moduli space of curves, as algebraic geometrists call it. So it's some central object in mathematics, it's a basic example in many fields. Okay, so and today's result is the fact that Teichmuller space is a cell, which actually kind of implies that this is indeed the universal cover of the moduli space. Okay, so somehow that's the sort of the gist of what I'm going to talk about. So anyway, that's the plan. So today, to construct hyperbolic metrics, let me start with the simplest sort of surface, namely the pair of pans. Okay, so here's a pair of pans. It's a 3-hole sphere. So in other words, it's S03. Okay, its Euler characteristic is -1. And I won't write S03 every time. I'll maybe call it P for pans. Okay, so how do you construct hyperbolic metrics here? So you do what any respectable tailor would do. They take two hyperbolic pieces and you sort of glue them to get the pair of pans. So you take two sort of identical right-angled hyperbolic hexagons. Okay, so these are some polygons that on the hyperbolic plane. Let me just draw them themselves. Okay, so here's one hexagon, and although my drawing won't be identical, so imagine that two identical hyperbolic hexagons, and how do you glue them? Well, you identify alternating edges. Okay, so these edges that I marked are identified. So you identify alternating sides. So the sides which are not identified, so after the gluing, so let me just draw what you get. So after the gluing, you would get 3 boundary components built up of these sides which you didn't identify. And these sides which you did identify give you the seams for these pair of pans. Okay, so get something like this. And if you started with a right-angled hyperbolic hexagon, by the way, I'll often abbreviate to RAHH. So suppose the lengths of these edges which you didn't identify are A, B, C. Okay, so then in the resulting hyperbolic pair of pans, these boundary components would have lengths 2A, 2B, and 2C. Okay, so the first thing is what numbers could these A, B, C take? I mean, what possible values? So here's the sort of the basic lemma that for any positive real numbers A, B, and C, there exists a unique right-angled hyperbolic hexagon with alternating sides of lengths A, B, and C. Okay, so the proof of this is some exercise in hyperbolic geometry. So let me give a sort of idea of the proof. So sort of a sketch of the proof. So the first claim is to specify a right-angled hyperbolic hexagon. It actually suffices to know 3 consecutive sides. Okay, so first instead of alternating sides. So let's give the other side some name or some length. So this is X, Y, Z. Say these are the sides which get identified when you take 2 copies and do them. But right now we're only looking at this one of them. So the claim 1 is that so if we know so 3 consecutive sides. Let's call it A, let's say A, X, and B. So determine the right-angled hyperbolic hexagon uniquely. Okay, and the proof of this is well, it follows from some picture in hyperbolic, on the hyperbolic plane. So let me just draw the upper half plane model. So here's what a hyperbolic hexagon would look like. So suppose one of the edges is along this vertical geodesic of length A. Then sort of there's a perpendicular geodesic of a segment of length X and so on. So you would so you would have some picture like this. So here's another Y, and so there's a Y, and then finally there's some C. Okay, so this is what a hyperbolic hexagon would look like on the upper half plane. Now, if you know 3 consecutive sides, so suppose so I tell you what A and this side of length X and this side of length B are, so these 3, then I claim that the rest of the sides are determined. How does it determine? Well, you know that you have to be, so all these are sort of right angles. So you drop perpendicular, this geodesic, let's say alpha, from the end point where B ends, and you drop this perpendicular geodesic from the end point of this side of length A, let's call it beta. And then the remaining side, so these sides of lengths Y and Z lie on alpha and beta, and the remaining side, length C, is the unique perpendicular geodesic between alpha and beta. Okay, so everything, all the picture is determined once you know A, X, and B. Okay, so that's sort of the, well, I just drew a picture, but you can, that's how this claim 1 is proved. Okay, so this is claim 1, and claim 2 is, so in fact, so if you keep A and B, these lengths fixed, and you vary X, then this remaining side, this side of length C varies continuously, and not only that, it varies, it increases as X increases. So it's monotonic in the length X. So claim 2 is that the length C is a continuous increasing function of the length X. So once again, I mean, you can probably guess in the picture. So if you increase this side length X, okay. So here, let me again remind you, I keep A and B fixed, okay. So if I keep A and B, these lengths fixed, but I increase X, so somehow you're continuing more along here, and this whole picture moves to the left. So the new alpha, let's call it alpha prime, is further away from this geodesic beta. And this perpendicular distance that determines this side length C is much more. Okay, and you can make this more precise. You can write down a formula for the length if you want. It's an exercise in hyperbolic trigonometry. And indeed, there's some value of X. If you on the other side, if you kind of decrease X, then there's some value for which this alpha and beta are asymptotic. Okay, so then your C would be 0. So the continuous this function is something which starts from some positive value of X and goes to 0 infinity. Okay, so let me put an open. Okay, so phi of X equals C, and so the claim is that there is such a continuous function which increases. Okay, so and once you have this, then I mean the lemma follows. This means that there is a unique value of X in this interval, so that your value is C. This is the value that you want. You fixed a C, and you want to find a hyperbolic hexagon with this remaining side of length C. Okay, so this proves that there is some such unique hyperbolic hexagon. And a corollary is that for any positive reals A, B, and C, there exists a hyperbolic pair of pants with boundaries. The boundaries are always geodesics, as I said, of lengths well, 2A, 2B, and 2C. Okay, so you indeed get so any sort of three lengths, and in fact it's also unique. So you can kind of, this is how you can construct any hyperbolic pair of bands, because given a hyperbolic pair of bands, so let me just say conversely, so maybe I needed these hexagons. Let me just quickly draw them again. So conversely, so if you start with a hyperbolic pair of bands, so conversely, so if you so if you start with a hyperbolic pair of bands, how do you get two hexagons? Well, you can cut along the shortest arcs between the boundary components. That's always going to be a geodesic arc that's perpendicular to those geodesic boundaries. So, and you can cut along them. You can cut along the shortest arcs between the geodesic components. And if you do that, then you get two hexagons, and they are going to be identical. Why? Because they're going to share three alternating sides, namely the ones that you've cut along. Okay, and by the we've seen that once you specify three alternating sides, the hyperbolic hexagons are uniquely determined. So in this time, it's these three sides x, y, and z, and so these hyperbolic hexagons are indeed isometric. They're the same. Okay, so you can create any hyperbolic hexagon this way by this construction, and this therefore there's this uniqueness. I should also say that I need a little bit more. I need to label the boundaries. I need to be able to say which boundary is length 2A, which 2B and 2C. Otherwise, there's some kind of ambiguity of order 3. So I should really put here, so with not just boundaries, but labeled boundaries. Okay, so a consequence of this is the fact that, consequence of what I discussed is that the Teichmuller space of a pair of bands and I'll define Teichmuller space in general later, but for now you can think of a Teichmuller space of a pair of bands are all hyperbolic metrics, or all hyperbolic pairs of bands with labeled boundaries. Okay, so with a labeling of boundaries. So such things we saw are determined by these three real numbers, real positive numbers. So that's equal to R to the 3. Okay, so I could have written R plus to the 3, but this is homeomorphic to R to the 3. Okay, so this is sort of the first kind of Teichmuller space that we've seen. Okay, so what's the next sort of simplest surface? So the next simplest surface, let's move to sort of the next simplest case. So that's the one-hole torus. Okay, so here's what it looks like. In other words, it's S11. Okay, so again, its Euler characteristic is -1. So we want to do the same thing here, but this time we need some more curves to sort of cut along, and so we need this definition. So let me define a marking of on a one-hole torus. Let's call it T, is a choice of a homeomorphism. Let's call it F from this fixed surface one-hole torus is topologically, we fixed it, S11, to our given one-hole torus T. Okay, so that's a notion of a marking, and this again, it generalizes to any surface. It's just a marking is a choice of a homeomorphism to our surface that's given to us. And we say that two markings are equivalent if they are homotopic to each other. So if they are isotopic one, either one. Okay, so we kind of need this notion. So now this is a more general notion, as I said. So let me give some examples of markings for much simpler surfaces. So, so for example, if you look at sort of the 0th example, perhaps is if you look at S01, this is the sphere with one hole. That's just the disk. Okay, so if you take a closed disk, so what are markings of a closed disk? So what are homeomorphisms up to homotopy? Well, it turns out there is only one. Okay. By the way, I should have also mentioned that here, this homotopy, you allow the boundary points to move. The boundaries have to be preserved as a set, but you're allowed to, during the homotopy, move points in the boundary. They're not required to fix it point-wise. Okay, so this definition varies from place to place. So if you're looking at a disk, then homeomorphism of a disk is always homotopic to the identity. So on the boundary, you have a homeomorphism of the circle, which you can homotop to be the identity map. And then you can radially extend that to be an identity map on larger and larger annuli around the boundary and eventually the disk. Okay, so there's a homotopy to the identity map. So there's only, so D2, there's a unique marking on D2. Okay, so there is, so if you think of markings as homeomorphisms up to homotopy, there is a unique marking. Okay, so what about the sphere with two holes? So that's just the annulus, right? So if you look at an annulus, or a cylinder, so what are possible markings of a cylinder? Well, so there are sort of two possible markings. Okay, so you can either preserve these boundary components, or you can swap them. Okay, so so you have two markings. So either you have sort of F is homotopic to basically the identity map, or it's homotopic to something like a pi rotation, okay, which rotates and sort of swaps the boundary. So you can prove, yes? Yes, okay, so I should have mentioned here, yeah, you're right. I should also said this is orientation preserving. Okay, so all our surfaces are oriented. Okay, we'll only look at sort of oriented surfaces. Okay, so thanks, yeah, okay. So there are two markings here. So the F is either the identity or the a pi rotation. Okay, so these are these both orientation. Okay, and similarly, so let me not write too much, but for a pair of pants, so the only sort of possible markings amounts to these labeling of the boundary components, what you've already seen. Okay, so here you can think of this as labeling of the boundary components as defining a marking for the annulus, and so here it's sort of there are three possibilities and the labeling of the boundary. Okay, so that was for these kind of simple surfaces, but for a one-hole torus, that actually turns out there are plenty of markings, and a fact is that so if you fix generators, the fundamental group of the one-hole torus, okay, let's call it S11. Okay, so so you know what these generators look like. There are these two curves; they're transverse to each other. Then a marking. So marking is a homeomorphism to our given one-hole torus, T. A marking is determined by where these curves go. Okay, so So maybe this, I don't know, this B map somewhere, we call it beta, and alpha might be sort of, might twist around a little bit. Be some pair of curves, again, they intersect once, it's like here because it's a homeomorphism. So a marking is determined uniquely by the images. And I give the image curves a name. So alpha is sort of f of A, and beta is f of B. Of course, you only care about the images up to homotopy again. So all these sort of things, you only care about the homotopy class. Okay, so, and the proof of this is, again, I mean, so how do you see this? Well, if you cut along A and B, you get an annulus. In fact, it turns out, if you imagine, it's similarly, if you cut along, oh, sorry, I called it. So alpha and beta, then you also get an annulus, and you're reduced to this case of an annulus. Okay, so homeomorphism anyway preserves this boundary component, and the other one is, so you can reduce it to the case of an annulus. So these choices of alpha and beta determine the marking. So you can, if you think of a marking on a one-hole torus, you can forget about this f, and you just think of these two curves, a pair of curves that intersect once and generate the fundamental group. That's an example of a marking. Okay, so we need this. So how do you construct? So how to build a marked hyperbolic one-hole torus? Now you want to build a hyperbolic metric and a marking on a one-hole torus. So let's say, let's call it T on T. Well, like before, you want to sort of build with this, start with a simpler surface. So you take, this time you take a pair of pans, a hyperbolic pair of pans. These you already know about. And with the two boundaries of equal length. Okay, so with two, so let's say boundaries 1 and 2 of equal length. So this is what it would look like. I mean, so maybe this is one of the boundary components, and there are two others. So maybe this has length L prime, and this is L and L. Okay, so you start with such a hyperbolic pair of pans, and the way to build to get a one-hole torus out of it is to then identify these two boundaries. Okay, so identify these boundaries of equal lengths. Okay, so boundary components 1 and 2. Okay, so if you identify them, then you would get, well, so there'll be a boundary of length L, and this L prime, and then this, these have gotten identified to some closed geodesic on a one-hole torus. Now, except that now you have this identification, you're gluing two circles of the same length, you have some freedom. So namely, you can rotate relative to each other, okay, before gluing. And so this identification, you also have to specify a twist. Okay, so identify boundary components 1 and 2 with a twist. Okay, so you're allowed to, so when gluing, sort of twist one boundary relative to each other. And this is something that you have to measure. So let me describe how to measure this twist. So what you need are some kind of reference points on these circles with respect to which you measure this twist. And that's provided by, if you look at the shortest arc between these boundary components, let's call it gamma perp, it's always going to be perpendicular to these boundary components. So the endpoints of these would provide some kind of reference points on these boundary geodesics. Okay, so you pick, so you fix, so let gamma perp be the shortest arc between these boundaries 1 and 2. So then a zero twist is when the endpoints of gamma perp line up. Okay, so when you identify these, so this endpoint and that point sort of match up, and you get a closed geodesic in the resulting hyperbolic one-hole torus. Okay, so that's the case of a zero twist. And what about a positive twist? A positive twist is something where the pictures over here. So let me zoom in a bit here. So here you have one side of this boundary component, here the other side, and this gamma perp, one of these looks like this. And so when the endpoints don't line up, okay, so you imagine you're sort of bringing them close together and identifying them. So if the endpoints don't line up, but they differ by some distance t, okay, then that's a positive twist, and the value of the twist is t, okay? And this positive or negative depends on the orientation, so if whether these endpoints lie to the left or each other, or clockwise of each other, or not, and that's well defined, okay? Things are sort of surfaces oriented. The negative twist would be something that looks like this. So if you have, so this is the picture near this boundary components. So if this gamma perp comes down here and comes down there, and there is a distance t this time on the other side. Okay, so between the endpoints. So that's the twist parameter. This time you consider this to be a negative twist. Okay, so this is a signed distance. So so that completely specifies those three numbers. You start with a pair of bands, two boundary lengths equal, so you have two parameters, L and L prime, and you have one more, namely this twist, this distance by which you rotate. Yes? Yeah, I'll come to that. Yeah, your t can be anything. Yes? Yeah. Yeah. I'll come to this right now. So, so it turns out that I haven't yet told you what the marking is. Right? I told you that we want a marked hyperbolic metric. I forgot the word metric here on T. Okay, so far this kind of completely specifies the hyperbolic metric. Okay, so you've started with a pair of pens, and I've told you how to glue it. That's the hyperbolic metric. What's the marking? Where does the marking come from? Well, the marking, you take one of the curves. Remember, to define a marking, I just need to tell you these pair of curves, alpha and beta, which intersect once. Okay, so here, this alpha you take to be the identified boundary component. So identified boundary. So this is this one that you have this two boundary components, 1 and 2. Right? The one is sort of ignored for purposes of gluing. So the 1 and 2 identified, and that builds one of the curves. And beta is going to be built by closing up this gamma perp. So remember, so when there was a zero twist, this gamma perp closed up to be this curve. When there's a mismatch between endpoints, you add an arc along this boundary, okay, between the endpoints. So beta is going to be homotopic to gamma perp union an arc along alpha in the correct direction, depending on sort of oriented direction, depending on whether it's a positive twist or negative twist, of length t. Okay, I mean, so I should really say sort of the positive t, this length, or if you're thinking of signed distance, I need not put this, but you close up these endpoints with this arc. So that this pair, alpha beta, is a pair of curves that intersects once. Okay, so it's going to be something on the surface that generates a fundamental group. So this determines a marking. And now comes this question of the 2 pi and all. So if you if you allow your t to be really positive, okay, so a very large number, okay, then all it means is that this marking, so after gluing, so remember that these endpoints have to be joined by a curve, an arc that goes along alpha, a distance t, which is maybe very large. So that would be homotopic to the beta. So alpha and beta, we only care up to homotopy anyway. So let me draw it sort of a bit spaced out. So here, this curve might twist around this cylindrical portion that you see when you zoom in many times. Okay, so that is what this new marking would be. So the marking here would be different once t crosses 2 pi. Every time you cross the length of this geodesic, not just 2 pi, it's the length of this geodesic, then you pick up a new twist. Okay, so you're changing the marking. The hyperbolic structure comes back to where it was, but your marked hyperbolic structure is different. Okay, so that answers the question. So that's so one way. So if you kind of you have these 3 parameters L, L prime, and T, you can build a marked hyperbolic torus. Conversely, so if you want to start with, so let me go here. So so if you start with a marked hyperbolic one-hole torus, so this is a marking, so you're given this, and you have a hyperbolic metric on here. So conversely, so given a marked hyperbolic one-hole torus, so what you can do, how do you sort of, so you can sort of reverse these steps. So you can cut along alpha. So actually, let me sort of swap the alpha and beta here, so easier to see. If you cut along this curve, you get a hyperbolic pair of bands. Okay. By the way, so when I say cut along alpha, I would really mean so I remember alpha is determined up to homotopy. So I pick the geodesic representative in the homotopy class. Okay, so you cut along a geodesic, you get a hyperbolic pair of bands with the same boundary lengths here and some other length here. So these give you, so this alpha, after cutting, this gives you these 2 parameters. And how do you determine the remaining twist parameter? Well, so the other curve, beta, will be some arc in this picture. Maybe it twists around here a few times and sort of hits back alpha. So it only intersects alpha once. So that's what beta after cutting looks like. Well, this beta is going to be homotopic to gamma perp. This hyperbolic pair of bands would have a perpendicular geodesic between the boundaries. It would be homotopic to the gamma perp union some arc along alpha of length t. Okay, so there's always going to be some such arc, and this twist parameter would be equal to t with a sign depending on which way you orient that arc. Okay, so whether you want a positive twist or a negative twist. All right, and so this process kind of is a sort of the converse, the reverse of this, and this determines 3 parameters, L, L prime, and T. So, and these can completely specify this marked hyperbolic one-hole torus. Okay, so so a consequence of this is the fact that the Teichmuller space of a one-hole torus of one-hole torus is 1, 1. We call it which is the space of all hyperbolic metrics on S11, together with a marking. Okay, so together we want marked one-hole tori. So together with a marking. So that's what a Teichmuller space for torus would mean. So that is again equal to R to the 3, because you have 3 parameters which compute it. Okay, so so in general, so let me now sort of define Teichmuller space of a surface. So, so the Teichmuller space of SGB, I'll denote it by the script T, SGB. So that's going to be hyperbolic metrics on SGB, hyperbolic surfaces, together with markings. So here X is a hyperbolic surface, and F from SGB to X is a homeomorphism. That's our marking. And up to an equivalence. So the equivalence is that two pairs are equivalent, or the same point in Teichmuller space, if the surfaces are isometric and the markings are homotopic. So here's what a pair would look like. There'll be a map from this fixed topological surface to X, and here's another marking to Y, and they are equivalent if and only if there is an isometry between X and Y. There's an isometry here, let's call it I, such that this composition F followed with I is homotopic to G. Okay, so in other words, these surfaces are the same isometrically, and the markings are homotopic. So that's the more general discussion of definition of Teichmuller space, which subsumes these things which I stated for the hyperbolic, for the space of hyperbolic metrics on pairs of pans and one-hole tori. This is general. Okay, so so the main theorem I want to tell you is the fact that Teichmuller space of, just like these special cases we've seen, in general, Teichmuller space of a compact surface genus G and B boundary components is equal to, this homeomorphic to, R to the 3 times the absolute value of the Euler characteristic. So let me just write it out. So here, if you kind of expand 6G minus 6 plus 3B. Okay. So we are going to do all these constructions we've seen in this more general setting. So the first thing to start with is a pair of pans decomposition of the surface SG. So let me say what that is. So it turns out that if you start with this compact surface, SGB, so this can be decomposed into 2G minus 2 plus B pairs of pans. Okay, so let's look at, for example, just to have a picture, so the surface I drew at the very beginning. So you have genus 2 and 2 boundary components. Looks like this. Maybe let me draw it somewhat differently. Okay, so then how do you decompose it into pairs of pans? So pairs of pans will be our building blocks, okay, for this hyperbolic metric. So you can sort of throw in curves which are disjoint and simple closed disjoint curves which are sort of distinct. So no two are homotopic to each other. Then you will build a collection of pairs of pans. Okay, so this pairs of pans are cut along a maximal collection of disjoint simple closed curves that are non-trivial in homotopy, and there are pairwise non-homotopic, let's put it this way. So this is how you build a pair of pans decomposition. There are these many pairs of pans because all the characteristics add up when you're gluing, and so a pair of pans is all the characteristic minus 1. So that gives you this number. How many such curves are there? So these are, by the way, these are called pans curves. I'll call them pans curves. You can do a calculation. So each pair of pans would have sort of 3 sub-boundary curves, and if you do this, you count, except the boundary components, you count each curve twice. If you multiply by 3, these pairs of pans, and so if you do that calculation, you'll find that there are 3g minus 3 plus b pans curves. Okay, and together with these boundary components, so you have these many, and plus you have these b boundary components. And so there are these many curves that you can see in the picture, and so if you cut along these, you get 2g minus 2 plus b pairs of pans, and this surface is obtained by gluing them along these pans curves. So there's some curve missing, right? Yeah, so here we need one more. Okay, so let me put this here. Okay, so if we cut along this, so you get some bunch of these pairs of pans, and you kind of recover this original surface and glue them. Okay, so that's what a pair of pans decomposition is. Okay, so a heuristic is the heuristic count for this now, so you can guess why do you have 6g minus 6 plus 3v. So the heuristic count is that for each, so remember that you have to now sort of, once you have these pans curves, you have to specify a hyperbolic metric on each. So that will be the lengths of all these pans curves. So you have a length parameters, which are number of these curves that you see. So together with these boundary curves, you have 3g minus 3 plus 2b such lengths. Okay, and once you have a pans decomposition, you recover a hyperbolic surface, you would need to glue them together, and that is an additional twist parameter for each of the these pans curves. Okay, not the boundary components. The boundary components don't feature in this. So there's these twist parameters, which are 3g minus 3 plus b of them. And indeed, if you add these up, you get this number. Okay, so that is what we are going to aim for. So how do you prove this? So how do you sort of measure these twists and so on? So the proof of the theorem. So why is the Teichmuller space exactly equal to r to the 6g minus 6? Sorry? No, I haven't. So there's always a plus b in the pans curves already. Okay, so if you count the number of pans curves, the ones I've drawn here in this different color, not the boundaries, you actually have a plus b already. Okay, so it's just an exercise in counting. Okay, so so there's no twist about the boundaries. That doesn't make sense because we are defining things up to homotopy that allows the boundary to kind of move. Okay, so any twist on the boundary, you can untwist. That's going to define the same point. So that's okay, so the proof of this theorem is as follows. So you fix a pair of Pan's decomposition. So fix a pair of Pan's decomposition. So this collection of such curves, 3g minus 3 plus b curves of this compact surface, SGB. So this will give a picture like this. It will sort of, if you start with a hyperbolic surface, you have these hyperbolic pairs of Pan. Now to measure these twists, we need something more. So we need to fix these, something like those perpendicular, these geodesics that we fix, these arcs that we fix. So we also fix an auxiliary set of curves, simple closed curves, sort of beta gamma for each Pan's curve gamma that intersects each Pan's curve gamma once. So what are the pictures? So as shown. So let me draw the two pictures. So in case one, suppose you have a Pan's curve which is not separating. So this is what it might look like. So there's the rest of the surface which I'm not drawing, and suppose there's a Pan's curve gamma which looks like this. In that case, the auxiliary curve that you choose is something beta gamma that intersects gamma once, okay, in this one-hot torus. And case 2 is, suppose this curve gamma is separating, the Pan's curve is separating. So then maybe the picture looks like this. Then you choose your auxiliary curve to be this beta gamma. Okay, so that looks like this in the picture. It intersects gamma twice. Okay, so you fix once and for all on your surface SGB a Pan's decomposition, a set of Pan's curves, and these other set of curves intersecting the Pan's curves. Okay, so from this you can find this length and twist parameters. So maybe let me continue here. So this time I'll start with a marked hyperbolic surface. Marked hyperbolic metric on SGB. Okay, so given a marked hyperbolic surface X. So this is now we know what surface we are talking about in SGB. So what you do is, so you can define the length parameters. So you already have these pair of Pan's decomposition and these auxiliary curves. So the length parameters are the lengths of the curves of these Pan's curves. Okay, so I should say that there's a marking, right? So marking is throwing these curves that you have on SGB to your hyperbolic surface. Okay, so the marking is this homeomorphism. And on the hyperbolic surface, for each of these curves, the resulting Pan's curves that you get, you can homotope them to a unique geodesic. Okay, and it's those lengths that you count. So the lengths of the geodesic representatives in the homotopy class of the curve f of gamma for each Pan's curve gamma. Okay, so this is what I said. So this f is our marking. Okay, so the marked hyperbolic surface is actually a pair x comma f. Okay, in Teichmuller space. So given such a thing, so from this gamma belongs to our fixed topological surface SGB. You can use f to throw it onto this x, and then you look for the geodesic representative. and you record its. Okay, so these give you these length parameters, and there are indeed 3g minus 3 plus b of them. So what about the twist parameters? So this is what, again, you have to sort of try to define. But we've already seen this one-hole torus case, so now it will be easy. So, so twist parameters, so divides into two cases. For something, a pair of pans, or a pans curve in case 1, okay, so where it was non-separating. So here's the picture. So you're on the hyperbolic surface. Let me call this f gamma to be alpha gamma. So I'm going to denote this. I'm not going to write f gamma every time. So this curve alpha gamma is the Pan's curve when you think of it on the hyperbolic surface. Okay. So if for case 1, you have this picture. You have alpha gamma, and you also have so the curve beta gamma, which is sort of the image of our curve B, this transverse curve B gamma under the marking. Okay, and once again, this geodesic representative would live somewhere here, and it might cross. So it might twist around a few times, but it crosses alpha gamma once. Okay, so on the hyperbolic surface X, this is what this picture looks like. Okay, so the rest of the surface I'm not drawing, but this is what the picture looks like. So in case 1, how do you measure the twist parameter about alpha gamma? Well, if you cut along alpha gamma, you get a picture that looks like this. This is something you've already seen now, and we talked about the one-hole torus. So you have alpha gamma and alpha gamma. You have these two resulting boundary components of the same length. And you have this beta gamma that kind of maybe twists around here. So just like before, you can declare that the twist parameter equals T, where so our beta gamma is homotopic to so sort of alpha gamma perp. Okay, there will be some shortest arc which is perpendicular to these two boundary components, and there's going to be a unique arc along alpha gamma of length T, so this beta, the alpha gamma perp union, that arc is homotopic to beta gamma on the surface. Okay, so this is so over here this is on X. Okay, and this length T of this arc is going to be a twist parameter. Of course, there's also going to be a sign depending, and so the sign depends, just like before, on the orientation of the arc that you have to pick. Okay, so in case 1, this is how you measure the twist parameter corresponding to gamma. Okay, so you use this transverse curve beta gamma, B gamma, and its image beta gamma, and you kind of measure the twist this way. Okay, so similarly in case 2, so now the picture looks like this. So in case 2, so on the hyperbolic surface, you look at the image of the Pan's curve gamma. It might, and you look at its geodesic representative, it might look like this. That's our alpha gamma, and beta gamma would be perhaps, I mean, maybe it will twist some number of times around alpha gamma. Let me not try to draw that. This is beta gamma is something transverse to this. And so how do you, again, measure the this twist around alpha gamma? Well, you look at, you cut along alpha gamma as before. So this time you get sort of around this geodesic, you have these two pairs of pans. Okay, and this time you look at this alpha gamma perp. So these are two copies of alpha gamma, these boundaries. Alpha gamma perp, so there's this gamma 1 perp, and gamma 2 perp are now going to be shortest arcs between the same boundary components, which is not homotopic to the boundary. Okay, so you sort of you cut along alpha gamma, and alpha gamma 1 perp and alpha and gamma 2 perp are the shortest arcs with endpoints on alpha gamma for the resulting two pairs of pans, okay, the hyperbolic pairs of pans, okay, adjacent to this alpha gamma. Okay, now on the glued up surface, so what would they look like? So let me sort of use different colors. So here you have gamma perp orange, so maybe it might look something like this. Okay, these are the perpendicular arcs. Okay, so remember that the shortest arcs are always perpendicular to the boundary components. Okay, so this is basic fact from Riemannian geometry. And so this time, so first of all, the fact is that the endpoints of these shortest arcs will always bisect alpha gamma. Okay, so the length, so if you look at this shortest arc, this alpha gamma curve is going to be divided into two arcs of equal length. Okay, this is an exercise in hyperbolic geometry again. So you can prove that so these lengths are going to be the same. So the beta gamma, so the twist parameter is going to be measured by the arcs you need to close up these perpendicular arcs to build beta gamma, okay, something homotopic to beta gamma. So beta gamma this time is homotopic to gamma 1 perp, union an arc along alpha gamma, union gamma 2 perp, followed by an arc along alpha gamma again. Okay, so if you look at this picture, if you follow gamma 1 perp, you have to go along alpha gamma, follow with alpha 2 perp, and then again alpha gamma. Okay, so the resulting closed curve would be homotopic to beta gamma. And you might, if beta gamma twists around alpha gamma many times, you might need to, these arcs may need to go around alpha gamma a few times. Okay, so, but this fact actually tells you that the lengths of these arcs are the same. So the lengths are identical. And these lengths are equal to this twist parameter that we define. Okay, so there is indeed again a well-defined twist parameter. These lengths of these arcs t, on both sides there will be some opposite sides. There's some kind of symmetry. There will be both of the same length, and this we declare is the twist parameter. Okay, so in case 2, the twist parameter is this. Equals plus or minus t, where again the sign depends on which way this arc goes. Okay, so either it's clockwise or anti-clockwise. Okay, so this gives us for each Pan's curve a twist parameter, and you already have these length parameters, and so together, so I should say that there's also a length parameter for each Pan's curve and also the boundary components. Okay, so there are B boundary components. Those also contribute to the length parameters. But the twist parameters you have for each Pan's curve. Okay, so this gives us, so as a consequence, you have, these parameters, the length parameters, which are 3g minus 3 plus 2b of them, and the twist parameters, which are 3g minus 3 plus b. Okay, and so so that gives us one direction of this theorem. Okay, so given a marked hyperbolic surface, and once you fix this pair of Pan's decomposition as the auxiliary curves, you already have, let me not erase this theorem, you already have these many parameters. And conversely, if you start out with these set of parameters, remember that you fixed a pair of Pan's decomposition already, so once and for all. Okay, so if you, conversely, given these 6g minus 6 plus 3b parameters, you can construct firstly, you can construct a hyperbolic surface, a hyperbolic metric on SGP by gluing these pairs of pans. So these length parameters determine the hyperbolic pairs of pans uniquely. Okay, and these twist parameters give you instructions how to glue their boundaries. Okay, so how much of twist you need to do. So this hyperbolic metric is obtained by, so the length parameters, let me just write down what I said. So length parameters determine 2g minus 2 plus b hyperbolic pairs of pans. And the twist parameters determine their gluing. So you find a hyperbolic metric on this resulting on the surface SGP. You also get a marking. How does the marking come about? Well, there's a unique marking that takes the Pan's curves and the auxiliary curves. So these are curves that you've fixed on SGB to our alpha gamma and beta gamma. So remember that you have in this hyperbolic surface, you can build these beta gamma this way. Okay, so now you're starting with these pairs of pans. So you can build beta gamma which looks like this. So you know the twist parameters. So you go along alpha gamma some distance, and you close up. You get beta gamma. So you get a bunch of curves on the hyperbolics on the resulting hyperbolic surface, and there's these curves. If you cut along these, you actually get a bunch of disks or annuli, and then in fact there's a unique marking. There's a unique homeomorphism from your fixed topological surface to the hyperbolic surface that takes the Pan's curves and the auxiliary curves you've fixed to our given alpha, gamma, and beta. Okay, so that determines. So once you know these 6g minus 6 plus 3b parameters, it determines a marking as well. Okay, a marked hyperbolic. So this together now kind of proves as you've proved a sort of a bijection. So there's a so we proved that there's a map from Teichmuller space to, the length parameters are r plus to the 6g minus, so 3g minus 3 plus 2b. And the twist parameters can be any real number, positive and negative, plus 3b. So that's the same as homeomorphic to this. So there's such a map, which is a bijection. So, which is bijection. Okay, so there exists such a map. All right. So, so that's the parametrization of Teichmuller space. This is called the Fenchel-Nielsen parametrization. It depends on our initial choice of a Pan's decomposition and some set of auxiliary curves. Okay, so I should also mention that in fact, I mean, this is not just a bijection. So it's like a homeomorphism, but I haven't told you what the topology on the space is, and you can define it to come from this. Okay, so and it turns out to be independent of the choice of these Pans curves and so on. So so let me just note here that so remark that we shall assume. So in the next couple of lectures also, we will assume that the topology, that Teichmuller space acquires a topology via this this parametrization phi. Okay. One more thing to note in this topology, and this is going to be useful for us later. So let me say it as a fact. I won't prove it. But so is that in this topology, length functions are continuous. Okay, what's the length function? Well, if you fix a curve alpha, which is a simple closed curve, let's say, on SGB, then there is a length function defined on Teichmuller space, which is a function from Teichmuller space to positive reals. And what does it do? Well, it assigns, so suppose you're given a marked surface, let me write it as a pair. This is assigned the length of the corresponding curve on hyperbolic surface. Okay, the obvious thing that we've already seen, that curves, you throw it onto the hyperbolic surface and find the geodesic representative. So I'll just write it as length of f of alpha on x. Okay, and so these functions turn out to be continuous in this topology. I mean, of course, if you start with a curve alpha, which is one of these Pans curves, then you are, of course, it's a continuous, one of the coordinates. But in fact, so if you take any other curve on the surface, so it depends continuously on these parameters. If you kind of change these lengths of these pairs of Pans or these twists, the length of any other curve will change continuously. Okay, so this is what the content of this is, and this is some fact which we will use subsequently. Okay, so I'm out of time, but I'll stop here.